So on the past, I would say 8 exams, one of the first 5 questions or 6 questions, which are the calculator questions on your exam, have always been a word problem with logarithms or exponential functions. So what we're going to do now is we're going to look at some formulas. We've already seen the compound interest formula. We did that in an example earlier before we knew how to use logarithms. We just solved it with our graphing calculator. We also had like an altitude problem, which we had a formula that we solved with our graphing calculator. What we're going to look at now is a number of different areas that show exponential growth or exponential decay, and how they can be modeled with a function, and now how we can use logarithms instead of a graphing calculator approach to solve them. So we're going to use the skills that we've learned over the last little bit to solve them. So here's some examples of exponential growth. We've already talked about compound interest. Richter scale, earthquakes. What happens when you go from an earthquake that's a 7 to an earthquake that's 8? It's 1 bigger? It is 10 times bigger. So going from a 6 to a 7 is 10 times more intense. Going from a 7 to an 8 is another 10 times more intense. So going from a 6 to an 8 is 100 times more intense. So it goes up quite a bit. Same thing with decibels. Every time you're going up on decibels, it is not just 10 higher, it's like 10 times higher. Okay, so they're exponential in their, if you've done pH and chemistry, you've learned that something is 10 times more acidic each time you're going, or vice versa, or base. Exponential decay and half-life. Some interesting things here. Biology, some things decay. Radioactive substances. Some radioactive substances decay and change, and they have a half-life. So what the half-life means is that in a certain amount of time, half of it has changed. With your drugs in your body, this is an interesting concept, and an interesting thing to think about sports and drugs in your body for sport. How does that work? Sometimes you look at a bottle, you've got a headache, you take Tylenol, and it says, take 2 Tylenol every 4 hours. Well, what happens in those 4 hours is it might be the half-life of that drug. So I take 1,000 milligrams of Tylenol because I have a headache. My body uses up that drug, breaks that drug down. In 4 hours, I might have used up half of it. And so now I've got 500 milligrams of Tylenol still in my body, still working. But then I'm like, I still have a headache. I take 2 more pills. Now I add another 1,000. I'm at 1,500 milligrams in my body. 4 hours later, I still have a headache. But now, 4 hours later, if I take half of that out, I now have 750 in my body. So I take another 2 pills, I'm at 1,750. And if you keep doing this, what happens is you eventually reach a plateau. Eventually, my body will come to the point where I add 1,000 and I get to 2,000. But then when my body gets rid of half of it, I'd have 1,000 left. And but it means that you never get past a certain amount. And so the directions on the bottle is so that your body doesn't get too much of the drug in its body, in it at once. It also allows you to increase how much of the drug is in your body to help you with that headache later on. But it also says, don't start off with 4 because having that much drug in your body at the beginning might not be good for your system. So there's some interesting things that happen with the amount of drugs in your body and so on. So here's our first formula that we're going to play around with, our compound interest formula. You've already seen this formula. We've already done some questions with this formula. And it's an exponential formula because we've got one of the variables in the exponent. So if we're solving a question like this first one, determine the final value of $500 after 10 years if it is invested at a rate of 2.25% interest compounded monthly So on the exam, you would still have this formula. And in this formula, everything would be explained to you. So you would know what all of the variables stood for. And they could change the letters. You don't know what form of the formula you're going to get. I think our textbook used A0 instead of P for principal. And so in this case, we plug everything into our formula, and we realize what I want to solve for is A. Everything else is numbers. It's already on its own on the other side of the equation. So I can just plug this into my calculator and push enter. So what I'd like you to do is see, can you plug that whole thing into your calculator right now and push enter and get the same result? This same result that I got. And plug it in your values. Very straightforward. Some of the things that are hard here is figuring out, well, what does semi-annually mean? How many times per year is that compounded? So that would be twice a year. $232.11. So these first two examples, very straightforward. You could just type them into your calculator. No logarithms or any kind of fancy math needed. But in this next one, calculate the time it would take for an investment of $30 to double if it is compounded monthly at a rate of 7%. Again, I want you to take the time to do the first step, because that's where a lot of the thinking comes into place. Can you take the information in the question and get the right value down? How did you do? And now this is an exponential equation. And one of the things we're going to find with an exponential equation is, well, you see t and exponent, you've got the two techniques, get the bases the same or use logs. It might be pretty obvious in this one that you won't be getting the bases the same. But before we go too far into taking the log of both sides, what did I do from step 1 to step 2? I simplified it. Okay? By simplifying it earlier, that's going to make your life with logarithms a little bit easier. And in this case, dividing both sides by 30 ends up with 2. And we still have to solve for t. Now I want to take a moment before we solve for t and use our logarithms is just to analyze this and think about this a little bit. Let's say I reword the question. Calculate the time it would take for an investment of $300 to double. Well, how would that change my question? Instead of 30, I would have 300, and instead of 60, I would have 600. If I simplified this, what would I get? Exactly the same thing. And if I solve this for t, I'm going to get the same answer, right? So the amount of time it takes $30 to double is the same amount of time with compound interest that it takes $300 to double. Which is an interesting concept because if, I'm going to cheat and put a red dot there. 10 years. That's going to be our answer. Okay? Now we're going to go back up and uncheat. It takes 10 years for $30 to double to $60. It would take then 10 years for $300 to become $600. It would take 10 years for $3 million to become $6 million. And it would take 10 years for 3 cents to become 6 cents. Okay? So the time stays the same for doubling no matter how much money you have. So if you can convince someone to give you $3 million, I'll give it back to you in 10 years, no problem. and you can double it in 10 years, that'd be a very good idea. It's just, I've been working at it for a number of years, so still waiting for that person to just lend me $3 million with no strings attached. But those people are very hard to find. But if you find one, take advantage of that. Invest it, double your money, pull it out, and you'll have $3 million in 10 years. But it also means that the person has 3 cents, puts it away. Rainy day, 10 years later, goes to their bank account, opens it up, and pulls out 6 cents. Not quite as exciting.
That's a nickel.
Sometimes these questions, though, this is what I want to point out. Sometimes these questions say, calculate the time it would take for an investment, and then they don't give you this. An investment to double if it's compound. And you're like, Mr. JR, there's not enough information, there's not enough information. But you need to know, just like we did in this question, it doesn't matter how much money you had. So you can pick any number here, double it here. When you simplify, you get 2. And so that is the part that helps you with this question. Yes? You almost double it instantaneously.
Yeah. And then when you go 10 years later, 6 cents rounds down.
Yeah.
Would that be the same, like, say, like you wanted like a quarter, like, see how much, like, if it was like 30 was going to a quarter, it would just put any number.
You could put, and then the time is going to be how much it would increase by 25%. This would be 30. 25% of 30 is 7.5, 37.5. But when you divide it, you would get 1.25. Works out for tripling, works out the same amount of time no matter what you have. So sometimes these questions don't have a value there. And you need to know that because a lot of students without the value there say there's not enough information, don't solve the question at all, lose all 4 marks. So now that we have simplified it, and one of these things in these word problems, we are going to simplify if we can, because it makes us make less log mistakes when we solve. But you guys are already getting quite good at solving these. So we can now take the log or natural log of both sides. And when we do that, that 12t can come out in front. Because that 12t is an exponent to the entire thing inside of that log. Again, without simplifying it, you could take the log of both sides, but you have to be careful because if you take the log of this side with the 30, you're tempted to bring the 12t out right in front, but you wouldn't be allowed to because this is 30 times, and you'd have to expand first with the adding and then bring the exponent out in front. I want to get t by itself. So what would I have to divide by? I'd have to divide by the 12 and the big log thing. You can type that all into your calculator all at once. And you get 9.93 years. So if the interest rate was 7%, it's going to take roughly 10 years for something to double. And this, I'm going to teach you something called the rule of 70. And if the mental math doesn't work good, sometimes this rule is called the rule of 72. And the rule of 70 or the rule of 72 basically looks like this. Oops. Oh, just wait for it. There we go. Rule 70 or rule 72 looks like this. And it is a really simple formula. Right? That the formula itself does not look nearly as complicated as the compound interest formula. And it estimates, it doesn't solve, but it estimates how long an investment would take to double if the interest was compounded at that interest rate. So our interest rate was 7. Okay? Mental math, which is easier to divide by 7? 70 or 72? 70. So I put 7 in for interest rate, and I don't do a decimal, just 7. 70 divided by 7 is 10. What did we find out as our answer? 9.93. Oh, I hit the dot again. Dot, 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 dot. 9.93. Okay? If you had an interest rate of 6%, I would use this formula. 72 divides nicely by 6, comes out to 12. 6%, it would take 12 years to double. If you got 2%, well, either one of those is going to take a long time. 2% is going to take 35, 36 years for it to double. And so the rule of 72, or the rule of 70, gives you a quick estimate for how long something is going to take to double. Four years ago, Andrew invested in an RSP. The interest rate was 5% compounded quarterly. If it's now worth $2,500, how much did he originally invest? This is an easier question. Again, take the time, try and put everything into the formula. So we're solving for the principal, and in this case, all of our numbers, so I did the 4 times 4 to get 16 up here. All of our numbers, we're not solving an exponential equation here. So we do not need to use logarithms. We can just get p by itself by dividing both sides by that large value. I would type that whole thing in exactly as I see it into my calculator and get my answer. That's a very interesting amount that he originally invested. Next one, calculate the time it would take for a $200 investment to grow to $500. Compounded quarterly at an interest rate of 3%. So here we have an exponential equation. And since you guys are so good at solving exponential equations, I will get you to solve this first on your own. So here I didn't simplify. If you simplified, that's even better. So if you divided both sides by 200, you got 2.5 on the other side. Okay? But I want to show you that if you didn't simplify, you would have to first add here before you can bring that exponent out in front. And so this is why simplifying is nice, because it takes out that step of your log laws. The interesting thing is, can you see here when I subtract the log 200 to the other side, your log law for subtracting is dividing. And so you would get the 500 divided by 200 in that part anyways, or you can see why it's equivalent to the 2.5 that you probably have on your side. Type that all in. That's equal to t. And you get 30.66 years. Have to include the units.
Can we leave it as a fraction in our formula? Like, does it matter? Like, leave it as 5?
That is fine. You can leave it as 5 over 2, and when you take log of 5 over 2, it'll work out just the same. So if you did divide it to begin with, on the top the only difference is you have log of 2.5 or log of 5 over 2. But you got the exact same answer. So again, it's recommended that we divide first. How long does it take for an investment to triple? Some of you started this one already. Here's your setup. I just used 1 and 3. You could have used 10 and 30, 100 and 300. The time is going to stay the same to triple, no matter how much you started with. 372, and oh my goodness, now I have to multiply by 3. So choose a value that's easy to multiply by 3. And then simplify so you just get 3, because when you take the log of both sides, and then divide 22 years for something to triple. So if you have $1,000, 22 years, you'd have $3,000. That seems like a long time to wait, but at least it's in your lifetime. It's like, it feels like 220 years would be like, oh man, can't take it out yet. I'm just going to wait a little bit longer.
I like the
You like the approximation sign there?